So hello everyone, my name is Kamal and today I welcome you all to my YouTube channel. I request all of you please comment, like, share and subscribe to my channel. Today I'll discuss about microwave spectroscopy, also known as rotational spectroscopy. The energy involved in rotational spectroscopy or microwave spectroscopy lies in the range 30 to 300 gigahertz, and this belongs to the microwave range of electromagnetic radiation, electromagnetic spectrum. And so here I have given one example of carbon monoxide molecule. So two different molecules are there, carbon 12, oxygen 18 and carbon 13, oxygen 16. So this is the way rotational spectra or microwave spectra is represented. And this is lecture 1. So I will explain the outline of my lecture, but this is a lecture 1. Okay, let's start about, let me give a detailed content about how I'll proceed. So I have divided the whole course in 3 different lectures. Lecture 1 will consist of the brief introduction to moment of inertia, and then I'll classify different molecules. And in this video I'll talk about the microwave spectra or rotational spectra of rigid diatomic molecules. And after that, in the second lecture, I'll talk about the intensity of spectral line. Then I'll talk about the effect of isotopic substitution. And finally, I'll talk about the non-rigid rotors. So I'll jump from the rigid rotor to non-rigid rotor in lecture 2. And in the last lecture, I'll talk about the polyatomic molecules. For example, linear polyatomic molecules, and I'll also discuss about the non-linear molecules. And this will be the end of the lecture. Okay, about the course related to microwave spectroscopy. Okay. Let me start with today's lecture, which is about 3 different topics I'll discuss. Okay, now rotational spectroscopy or microwave spectroscopy deals with molecules when they are in rotational motion. So we are not worrying about translational motion or vibrational motion, which may also occur simultaneously, but right now we're only considering the rotational motion and ignoring all other motion. Now here I'm trying to explain what is moment of inertia, because this quantity is very important. In many of the equation you will get this quantity, moment of inertia. So let me explain what is that. Now here I have drawn one diagram, and this is kind of a disk which is rotating, and the axis of rotation is shown in the red arrow. Now what is moment of inertia? This is a question we are going to answer in this slide. Now it is a property associated with rotational motion of object. That means whenever you have any object which is in rotation, you have a property, moment of inertia, associated with it. Okay. Now how to determine that? Now the formula for determination is that, let us consider one particle on the disk which is having a mass m1 and the distance from the rotational axis. So we are considering the perpendicular distance is r1. Okay. Now if you multiply mass of the particle and the square of the distance, this quantity is known as rotation moment of inertia. Because this is a large object and this will contain many particles, so in order to determine the moment of inertia for complete object or complete disk, what I have to do, I have to add the moment of inertia for each particle. Okay, this is for m1, m2, so on. So I have to calculate for all the particles. Okay, and finally I need to add them. So this is the moment of inertia for whole disk. Okay, this is the definition of moment of inertia. So what you need the mass of the particle and the perpendicular distance from the rotation axis. So this is in brief about the moment of inertia. Now let us move our real chemistry application. Now, before discussing the rotational spectra of diatomic molecule, which is the topic of today's lecture, let me introduce about different types of molecules and how to classify them based on the how many moment of inertia, how many different types of moment of inertia they have. Okay. Now we are living in a three-dimensional world. So we have in principle three axes. Usually we call it X, Y, and Z. For conventional reason, we in rotational spectroscopy we define them like A, B, and C. Okay, so let us consider the molecules which are under rotation. We usually call rotors. Let's see how to classify the molecules based on different types of moment of inertia. First, we'll consider linear molecules. Okay, this is for the simplicity. Now, in linear molecule, you can see that there are three different directions I have assigned here. In the green color, this I have defined as IA, and this is rotation along the HCl bond axis. Okay, and there is another axis which I have drawn in red color. This is, you can see, uh, in the plane itself where the molecule also exists, and the name of this I have assigned IB, and another one IC, which is perpendicular to the plane. It is also passing through the midpoint. Now, if you see that rotation along this axis, the moment of inertia corresponding to it is very close to zero, although it is not exactly zero, but in as an approximation, we can take it as a zero. And the other two directions, the moment of inertia is same, because if you see, if you rotate along this direction, IB direction, the moment of inertia you will calculate will have a same value, because you have to take the distance from here, square it, multiply with the mass of the chlorine. Similarly, you have to do for hydrogen, and at distance, if you calculate from the blue axis also, it is exactly same. This is the reason why in both the cases, the IB and IC, the moment of inertia when the molecule is rotating along IB direction, and the moment of inertia when the molecule rotating along the IC direction is exactly same. So in this case, I don't have only one moment of inertia is enough for explaining the whole molecule, because IA is 0 and IB equal to IC. So I need only one moment of inertia. So that's why linear molecules are easier to understand. The rotational spectroscopy is easier uh, to understand for linear molecule. So here I have given some molecules, this OCS molecule and HCl molecule. So this is similar to your carbon dioxide, but you have to replace the oxygen by sulfur. Now, one important point I want to point out here, also I'll point out later, the permanent dipole moment. Okay, for microwave spectroscopy, you need to have a permanent dipole moment. You can have different moment of inertia, but for microwave spectroscopy, you need to have a permanent dipole moment. Okay, so this is one of the important conditions. Let's see other type of molecules. So as I discussed already about the linear molecule, let us now discuss about non-linear molecule. Now, in non-linear molecule, I have three different types. Usually we call it a symmetric top, spherical top, and asymmetric top. Now, what is symmetric top? In symmetric top, you can have IB equal to IC, but not equal to IA. That is, the moment of inertia along the B axis and the moment of inertia along C axis are same, but this is not equal to the moment of inertia along A direction. Okay. Now here two different conditions exist. IB and IC may be greater than IA, or IB and IC can be less than IA. Now this is one of the example where you have IB equal to IC greater than IA. Now if you have this kind of condition, then this kind of rotors or molecules are known as prolet. Okay, this is a described with the help of this common name. Prolet means you have IV and IC greater than IA. And another condition is that you can have IB and IC equal, but it is less than IA. Now, if you satisfy this condition, then this is known as oblet. So, in many exams, this question sometimes comes. They will give this kind of equation and they will ask that is it a prolet or oblet. So, you need to remember it, which one is prolet and which one is oblet, and based on that, you have to answer it. So, these are the conditions you need to remember. So, this is about symmetric rotors. Okay, these two types of systems are known as symmetric rotors. Now, spherical rotors. Spherical rotors means this is a molecule of methane, and all the four hydrogens are same. Now, in spherical rotors, all the directions are same. I should say that it is very difficult to define direction in spherical rotors. You can choose any direction. All direction looks same. So this is the condition for spherical rotor. Usually you will not get question based on spherical rotors because everything is same. There is no confusion. So the confusion comes here. And another type of molecule is your asymmetric top. In asymmetric top, you have all the three moment of inertia are not equal. Okay, the value of moment of inertia along the B direction, along the C direction, along the A direction is not equal. So this is known as asymmetric top. So I have explained that I can classify my molecules based on how many moment of inertia they have. Okay. For linear molecules, you need to define only one. In this case, in symmetric top, only two is good enough because IB and IC are equal. So you need only IB or IC and IA. In spherical top, all are same. So you need only one is good enough to explain your spectroscopic property. And then you have asymmetric top where you have a three different directions, all are different. So you need to have a three different moment of inertia. Okay, this is about the classification of molecules based on how many types of moment of inertia they have. Now let us start our actual calculation on diatomic molecule. So as I already said, in this video I'll talk about only the rigid rotors. That means, let me explain this graph to understand properly. So I have one molecule which consists of two different atoms having a mass m1 and mass m2. The mass of m1 is larger than m2. Okay. Now the distance between the atom will not change during the rotation. This is the condition of rigid rotors. That means while rotation, there is no change in the distance between the two atoms. Okay, that is the reason why we call it a rigid rotor. Now, as I already discussed in our classification, for linear molecule, I have IA equal to 0. That means the rotation along the bond axis will produce negligible moment of inertia. And I have the direction IB and IC, both are equal, so one of them is enough. So let us consider this is the direction along which I am trying to determine the energy of the rotational levels. And so to do that, I need to understand something about the distance and how they are related. So what is C? C is the point where it is known as center of gravity. Okay, the molecule is rotating along this direction. Okay, now this is the total distance between the two atoms R0, and they are related by R1 plus R2. Again, R1 is the distance from the center of gravity to the atom having mass m1, and the R2 is the distance between the center of gravity and the atom having mass m2. Now, at this condition, center of gravity This condition holds M1 R1 equal to M2 R2. Now, if I want to determine the moment of inertia for this molecule, which is rotating along this direction, what I have to do? Since there are two atoms, so I have to multiply the mass of the atom and the radius of the atom square. So the mass 2, radius R2 square. So both the atoms and the distance from the perpendicular distance from the rotation axis, I have to square it and sum it. Okay. Now, after doing some manipulation, what you get, you'll get the finally this result, I equal to M1 M2 divided by M1 plus M2 R naught, and this sum M1 plus M2 divided by M1 plus M2 is known as reduced mass, or it is represented by mu. Okay, let me again tell you. So what I did, you need to just replace this R1 by this sum. Okay, after solving this sum, you'll get one single equation for the moment of inertia. You don't have to have different equations. So finally, you will get moment of inertia is equal to M1 into M2 divided by M1 plus M2, and you have to multiply the R naught. So this is the distance between the two atoms. Okay, and this is usually represented by mu, also known as reduced mass. Now, if you do a quantum mechanical solution or Schrodinger solution of this rigid rotor, what you will get energy, and the energies are like this. So you have Ej h square by 8 pi square I j plus 1. So this is the energy of the rigid rotor, which I got from quantum mechanics or solving the Schrodinger equation for it. And you can see that energy levels are quantized. That means the energy levels depend on the value of J, and the J can take value 0, 1, 2, like that. And this is known as rotational quantum number. Fine. Again, I'm telling this is known as rotational quantum number. Okay. Now this is the energy for a diatomic molecule. Now let us plot the energies and see how it looks like. So this is the same equation which I have given earlier. Just let me remind you that this is in joule. Okay, this is very important. There are several units of energy. We need to absolutely sure about the unit, and this equation is in joule. But the problem is that scientists conventionally, in the research paper, they plot the or they give the spectra in terms of centimeter inverse. So no problem. This is a simple case. This is just a representation that I have changed from the joule to the centimeter inverse, and I am putting epsilon instead of the capital E. What I have to do, I have to just divide by this joule term with the help of HC. So finally, if you divide with the HC, one of the H will get cancelled, and you have IC here. Okay, and rest of the things are exactly same. There is no change, and it is more simplified. This big equation, this big term has been replaced by this simple B term. Okay, so this makes our life easy, and this is known as rotational constant. So this is one of the important property in many of the questions. You have to determine this. This is a rotational constant, and this is represented as the everything like h 8 pi square IC, and you must remember that this B has energy terms because this is a number, this is a number, everything is number. So the centimeter inverse coming only because of this term, and this is in centimeter inverse. Okay, this you must remember. Okay, you guys have to memorize this equation. Now let us plot that if you put J equal to 0, the energy is 0. If you put J equal to 1, what will be the energy? 2B. If you put J equal to 3, the energy will be 6B. J equal to 4, J equal to 3. If you put, you will get 12. If you put J equal to 4, you will get 20B, and 5 30B, and 6 42B. Okay. So these are the energy levels which I derived using this equation. Okay, let us now see the most important thing. That means where I'm allowing my system with the light. Okay, so this is the heart of my spectroscopy. I know the energy levels. Now I'm applying some electromagnetic radiation to my molecules, and what the molecules will do, and the molecules will absorb some of the energy and they will go to the excited state. Okay, now the problem is, and the most important thing is that permanent dipole moment. Not all the molecules can absorb microwave radiation. Only those molecules can absorb microwave radiation. Uh, those contain permanent dipole moment. Okay, and this is the important thing. You must keep in mind that the molecules which are which do not have permanent dipole moment, they are not microwave active. Only molecules which have permanent dipole moment, they are microwave active. And based on that and your interaction with the light, one selection rule has been derived. Okay, so there is a direct connection between this dipole moment and the selection rule, which I am not going to explain, but let me just I'm telling so that you guys will understand that there is a direct relationship between permanent dipole moment and the selection rule. Now, if you apply the selection rule, you can the molecule can do a transition from zero to, j equal to 0 to j equal to 1, but it cannot undergo a transition from j equal to 0 to j equal to 2 or j equal to 3 or j equal to 4. Similarly, it can go and it can undergo a transition from j equal to 1 to j equal to 2 and j equal to 2 to j equal to 3, j equal to 3 to j equal to 4, and so on. Okay. Now here I have derived the general formula. So whenever a molecule undergoes transition from one of the states, what is the general formula for the energy? And this is a general formula for the energy in centimeter inverse. Okay, this is only a way to write. Centimeter inverse we normally prefer to write in terms of wave number. Okay, this is a symbol of wave number, mu bar. Okay, let us see. That means if a molecule undergo a transition from j equal to j equal to j plus 1, the gap between them is 2b. Okay, so you can see here 2b j plus 1. If a molecule undergo a transition from j equal to 0 to j equal to 1, what is the gap? It's very easy to see. It's 2b. So if you put 0 here, you will get a 2b. Now, if j equal to 1 to j equal to 2, if you put j equal to 1, 1 plus 1, 2, 2 into 2b, 4. Also from the figure, it is very clear, 6b minus 2b, it should be 4b. And 12b minus 6b, it should be 6b. So if you see here, these are the peak position. Initially, you get at 2b. The second one you can get at 4b. The third one you can get at 6b. And the fourth one you will get at 8b. And the fifth one you will get it 10b. And finally, so this way you can calculate the position of the peaks in a microwave spectra or rotational spectra. So all come because of this selection rule. Delta J equal to plus minus 1. So please guys remember this selection rule. In many of the exams, only this question comes. What is the selection rule for microwave spectroscopy? Okay, and also permanent. This question related to permanent dipole moment also very frequent in the exam. Okay, let us now try to use the concept what we got and try to solve one problem. This came in CSIR exam, and this is like for a diatomic molecule AB, the energy for rotational transition from j equal to 1 to j equal to j equal to 0 to j equal to 1 state is 3.9 centimeter inverse. The energy for rotational transition from j equal to 3 to j equal to 4, how much? This is the question. So for simplicity or for better understanding, I have given a picture here again, and what they're asking for the j equal to 3 to j equal to 4. Let us first write down what they have given in the question. The energy for the j equal to 0 to j equal to 1 state they have given 3.9 centimeter inverse, and we know that the energy for the transition for from 0 to 1 is 2b. Okay, that means 2b equal to 3.9 centimeter inverse, and we will use this sum in our this equation. So we have to determine the energy from energy involved in a transition from j equal to 3 to j equal to 4, and from the diagram it's pretty clear that you can use the formula also, or you can directly use this diagram. What you get 8b. Okay, the difference between 3 and 4 is your 8b, and 8 I can write in this way, 4 into 2b. 2b already I know, 3.9 centimeter inverse, and finally I will get your 15.6 centimeter inverse. So the answer for this question is 15 centimeter inverse. So I have also put in the slide one quiz question for which came in the GATE exam. So they are saying that the j equal to 0 to 1 rotational transition for this molecule occurs at 500.72 gigahertz. Assuming that the molecule to be a rigid rotor, determine the energy for this transition. So please guys solve this problem, and you can put your answer in the comment section. And the important thing I will suggest that convert this gigahertz to centimeter inverse. So that is also a good exercise. Okay, use the same formula h nu equal to E equal to h nu. From there you can easily convert it. So once you get in the centimeter inverse, you can follow the same way how to solve it. Okay, exactly similar question, just the energy value is different in different unit. Okay, let's do another problem. This I have taken from the manual book. This is quite a long question, and it involves several information, and you need to understand have to go very slowly in order to explain this question. This is about the rotational constant for H35Cl is observed to be at 10.5905 centimeter inverse. What are the values of B for HCl, where the Cl is 37, and another one molecule where we have deuterium and 35Cl. Okay, so only one information is given. The rotational constant for this molecule is given. Okay, B, the value of B is given. So what I have to do? I have to do several things, but before that, let me tell you that in case of when you change the atom with the isotope, there is no change in the radius. So the radius is same, although the mass will change, but the internuclear distance is not going to change. Okay, so that is the key point to remember while doing this problem. Okay, now suppose okay, let me answer it. We have the rotational constant for this molecule. Okay, so from this molecule, what I can determine the moment of inertia for this molecule. Okay, from the rotational constant given in the molecule for this molecule, I can calculate the moment of inertia for this molecule using this equation, which already I have explained earlier, and this is coming out to be this much. Okay, now once I know this moment of inertia, with the help of this equation, I can easily calculate the radius, and I know that the radius is same for all the complex. Okay, there is no change in the radius for isotopic substitution. Now I know the radius. Initially I calculated the moment of inertia from the moment of inertia, I calculated the radius of this, and eventually this will be same for all the other two complexes. Now, with the help of this radius and with the help of this equation, this is already very easy to understand. This is a reduced mass for the, this is the equation for the reduced mass m1 m2 divided by m1 plus m2. Already I described. With the help of this equation, I can calculate the reduced mass for both of them. And once I know the reduced mass, I already know the radius, I can calculate the moment of inertia. Now, once I know the moment of inertia, I can easily calculate the rotational constant for both of them. Okay. So what we have done basically, we have provided rotational constant for this molecule, and from this molecule I can calculate the moment of inertia for this molecule, and with the help of this equation and the reduced mass I can calculate very easily. Finally, I got the radius, and sorry, and from the radius I can easily calculate the moment of inertia for all the molecules, other two molecules. And once I know this, then I can use the same equation again to calculate the rotational constant. Fine. So this is the way you have to go round and round to solve this problem. And all the things I have given here. Okay, so these are the usual things. Either you will get in the question paper itself, these things will be provided. So don't worry about these things. Okay, so this is about the rotational constant, very important question. Okay, let me just explain two more questions which also came in the CSIR exam, and these are very easy questions. If you know the answer, if you know about the concept of rotational spectroscopy, it is very easy to answer. First one is quite easy. Which of the following exhibit rotational spectra? As I already said, you need a permanent dipole moment. So when you have homonuclear diatomic molecule like hydrogen and nitrogen, there is no way you can get dipole moment, permanent dipole moment. Also, even though if you have a heterodiatomic molecule, you know that carbon monoxide molecule is linear, and the dipole moment gets cancelled. Okay, and finally you have C where you have dipole moment. Okay, so the answer for this is carbon monoxide, which is having a permanent dipole moment. And another, already I discussed the microwave spectrum of the molecule is 3 rotational constant. Which of these options are correct? So as I discussed, in case of prolate and oblate, which belongs to the symmetric top, you just need two different rotational moment of inertia. IB and IC are equal and is not equal to IA. So I need only two moment of inertia. Correspondingly, I will need only two rotational constant. Symmetric top, everything is same. So I need only one rotational constant. Asymmetric top, this is a situation. All the moment of inertia are not equal, and for each of them, you will get one rotational constant. So the answer is the symmetric top. So thank you, guys. This is the last slide. So if you guys have any doubt or any problem related to this lecture 1, the rotational spectroscopy, which I have discussed, so you guys can comment in the comment section, and if you have any questions related to it or anything not clear, please feel free to ask me. So thank you all for today, and please subscribe to my channel and like and share and comment. So this I request all of you. So thank you and bye bye for now. So I'll come with a lecture 2 soon.